Okay, I think we are good and we can start. So, as always, a very warm welcome to everyone who joined today our digital coffee break. Um, Most of you, or many of you, know me already. My name is Angela, and I'm responsible for marketing here at AppWorks. And for those of you who don't know AppWorks yet, we are a 100% subsidiary of Premium Aerotech and part of Airbus. We design, develop, and manufacture products that truly exploit the benefits of additive manufacturing. Before handing over to our speaker of today, which is Arnaud, some technical remarks. So, as always, whenever you have some questions or some questions arise, type them in the Q&A session you can see below your screen. And whenever Arnaud is finished with his presentation, we will start answering all the questions which arise. Yeah, so our speaker of today, as I told you already, is Arnaud. So for me, it's time to grab the coffee for you as well, lean back and listen to Arnaud, our speaker of today.
Thank you, Angela. So good afternoon, everybody. My name is Arnaud Rosenberger from AppWorks. So I'm working at the R&D department there, and I'm also responsible for our processes, so heat treatment and printing processes. And I would like to give you a little overview of what kind of quality assurance is performed, let's say, in the AM process. Here we'll focus a little more on just the additive manufacturing process, not any kind of post-processing or anything like this. And we'll look at some of the best practices of the industry and showing a little bit maybe some of the example of what we are currently doing at AppWorks, just to ensure that every part that we're delivering has the best possible quality. So if we start talking about quality in AM, what do we have to talk about? So if my next slide is coming, yes, perfect. So where to start? So the first question to ask ourselves is to ask ourselves, what do we want to achieve? So which quality targets do we need? And we will first come to the point where we have to define some high-level requirements in terms of quality. So we'll talk about first the quality of the raw material, or we talk about qualifying the whole process, or checking the repeatability of the system, and also the stability of the system. So these are some high-level requirements, but we also quickly come to a point where we have to list all the defects that we actually want to avoid there, and also all the countermeasures that we want to put into place. So with all of this coming up, it can quickly become a little bit messy, and we can be a little bit overwhelmed on top of this. So we need to put a little bit of order into this. But before doing this, the main point that I want to tell you is that on top of that, there's already existing norms in there. There are some bits of normatives here and there, but there's nothing that is covering the whole picture. So the main message that I want to convey here is that there's no consensual standards in terms of norm. Nothing is agreed by the whole industry as, let's say, the holy grail of quality in AM, which would tell you what to do, when to do it, and what to achieve there. So, and even those norms, they don't tell you actually how to do it. The currently existing norms, so there's already a few ones. So like there's some ASTM norms for critical applications, also some norms for characterization of the powder, some norms for all aerospace related product, but nothing overall. But that never tells you how to achieve it. They tell you what to achieve it and not how to achieve it. And this is why the knowledge of the process and how everything is happening behind it is really important there, and will help a lot in order to ensure quality in the products. So there has been already some big players in the industry. So if we talk about just Airbus, the NASA, or some big OEM or car manufacturers, they have set up their own qualification standards and qualification process. But there's never been any homogenization there. And that's one of the challenges. So for us as a part manufacturer, as a supplier for them, we have to comply to each and every one of those norms from every customer. So most of those customers were early adopters, so they really started before everybody else, and they have sometimes taken slightly different ways, and this makes the whole result is that nothing is really homogenized there. There's no consensus on this. So the challenge that is here is how to converge between some of the proven best practice and those already existing norms in order to make sure that everything is produced within the right quality. So we'll be diving a little bit more into this by looking at what I would call the AM triptych. So this is, let's say, the kind of base of every norm or even internal requirement by everybody who has started setting up standards there. So we are splitting the process into three. So the first thing is actually then the raw material. So that's the basic input there. The second one is the system. So on what are you manufacturing your part? On which machine are you manufacturing your parts? There's multiple suppliers there. And yeah, each system can be really different there. The third one, there's a little bit of a debate there on how to proceed. It can be either the process or the part. Either we can qualify the whole process, and then we are enabling to create multiple different parts there, or maybe for some more critical applications, we qualify a single part, and then we are sure that this particular part on this particular system with this material is according to at least all requirements there. So all of this works together, the system, the material, and the part. It forms a whole. And if one of these elements is missing and is not controlled, then there's a risk. If we're printing on a qualified system with a qualified process, but the material is maybe we just changed our supplier source and it has maybe a different chemistry, then the whole result can be different. Same thing if we change the system or if we change the process parameters, the whole end result will be different. So as an example, for us at AppWorks, maybe we have some qualified titanium powder from our supplier. We'll print on our qualified EOS M400 4 system, which is a defined serial number. So we don't qualify a family of machines, we'll qualify a single system there. And then we print with a qualified parameter set that we have proven over multiple months, even years now, and a lot of testing behind this. So we would print maybe with our 60 microns parameter on this system with this material, and then only after this, we have just the basis to check the quality of our products. So if we dive in a little more than on the first one, so the raw material, we will have then the approach we took there is to first look at the defects. So we could just also look at the already existing norms. There is already existing norms in there, but the nice exercise to do here is to look at what kind of defects are we expecting from our experience, from everything, all the parts we've manufactured, we've inspected and everything. What can we expect as kind of defects? And then from a, let's say, more bottom to top approach, then define what do we have to take, what measures do we have to take in order to tackle those defects. So, and we will see that there's kind of usually the same old friends appearing then, the same. So let's say the same defect can have different root causes. Can have one root cause in the material that can lead to microstructural defects, but also in the system that can lead also to the same microstructural defect. So if we look at the material, then we can have, I have listed, so this is not an exhaustive list, but I have listed 4 of the principal defects. So microstructure defects, so depending on the chemistry of your powder, so you don't have the right chemistry or the particle size distribution, it can lead to microstructure defects and also mechanical properties defects. So these are things that we can already tackle with some easy quality measures by having a supplier. So if you're purchasing the powder that has already norms defined on how to deliver this powder regarding the chemical composition, the particle size distribution, and thanks to all of this, you're already able to put a frame on top of this and make sure that your powder, at least your raw material, then is good quality enough that you can start printing on top of it. There can be a lot of other things that can come also then with just, let's say, the best practice of how you want to handle your powder. So the porosity, lack of fusion, and everything that can also be linked to to the process, but contaminations and inclusions can be also then, even if you purchase perfect powder, if you handle it in the wrong way, then you can have contaminations and inclusions. You have cross-material contamination if you're processing different materials in-house, also just by the tools that you're using, or there can be some wear on some steel parts that you have then some steel particles falling in your powder buckets. There can be a lot of things if you're not paying attention. So you need to have some really, let's say, good guidelines on how to handle the powder, to store it, there's a lot of things that are happening in there to make sure that we have the best quality. And all those things, you also want to minimize the risks that can happen there. So you will segment your powder batches. You will do things like define some lifetime of your powder and do some requalification. So you're gonna perform chemical compositions check on your powder. You're gonna even during the life cycle of your powder. So you have defined intervals after X builds or X amount of time, which one is the smallest. Then you will perform those checks again, which you already did when you received the powder. So that's it basically for the raw material. But we will also see one of the issue here is about the representativity. We'll find the issue also on nearly every of those three elements of this triptych, is how do you make sure that the test that you've performed is representative of everything? Here we have the issue, if we are sampling some of the powder, how can you make sure that the sample that you've taken is not, let's say, by luck, any luck, just good, and that the rest of the powder is maybe contaminated. Maybe you have just local contamination in one of your buckets of powder. Maybe there can be a lot of things happening that makes that the test you're performing is good, showing good results, but that the actual material that you're using is actually not the best, let's say. So there's also some guidelines on there to make sure that you have some blending in your powder, that you're homogenizing the powder every time between the builds, when you're merging batches, if you need to merge different batches, or when you're even receiving the powder. There's a lot of things there to make sure that you have then representative tests there. And all of this needs to be in complement, so tracked. So you need to have the right trackability to always be able to say, this print at this period of time was printed with this batch of powder, and keeping maybe storage of some samples of this powder if you anyway need to check it in the future because you have any concerns on a particular build. So that's it for the raw material. If we talk then about the system, then there can be multiple kind of defects. So first defect that come to mind is the porosity and lack of fusion. You can have the typical example that people talk about when we talk about defects on the system is obviously the laser. So the laser is the main element printing that is acting on the print. And if your laser power starts going down for whatever reason, so it's a lot of diodes there and they can randomly die with time, and so your laser power can go down. If your laser power go down, you will start having some porosity and lack of fusion, and this will be one of the big defects that can happen in AM there. Also talking about the laser, you want to make sure so that you have the right accuracy. So the second defect is the geometrical inaccuracy. It can be scaling, it can be just the correction map of your laser is not perfect. So you need, for all those defects, you need to have, let's say, proper maintenance there on your machine. So you can always do some checks yourself. So either by your machine supplier coming and checking your system, or a lot of checks can be done by yourself. So we can do laser power measurements. Usually in-house, we have tools to do this to make sure that in between each job, our laser power has not gotten down. Okay. Another defect is maybe worth to mention is on multi-laser systems. So we have overlap defects. So if you have 4 lasers acting together on the same part, you want to control also there that they are acting well in this overlap area, that you're not having too much of a shift, too much of a gap that would create then voids in your part, which could lead to cracks and then defects there. So this one is a little tricky to monitor, but usually you're able to check it, if not by by looking on the system, but by printing some tensile specimens in this overlap area, maybe, and checking the quality of those ones. There's also issues that you can have with oxidation or inclusions there. If you have, let's say, if your gas flow is maybe not strong enough, you can have sparks of the powder being melted that is falling down in the powder bed. You can have also, if your oxygen sensors are not calibrated well, you can have too high oxygen in your build chamber, and with reactive materials, then you will end up with oxidation. So there's quite a lot of things that can be checked on the hardware side on the system there. Other things that are worth to mention, I would say, are maybe the recoater and recoater plane. So you need to also make sure that your recoater is always well aligned. And this is something that the machine manufacturers cannot always check, because you will exchange your recoater usually before every build. So you need to have stable procedures also to make sure that the recoater is put on the system at the, let's say, on a horizontal angle at the, let's say, how it should be, and make sure that the plane where we're actually building the part coincides with the plane where the laser was calibrated on. So after saying all of this, it's quite clear that most of the defects can be avoided by maintenance in there and proper, let's say, best practice in operating the system. But it's not gonna make everything. You still need to actually then control your process parameters. So if we're talking about the process, there's a lot to discuss. As I mentioned before, there's, let's say, two kind of schools. We can either qualify the process or qualify the part. If we qualify the process, we are able to print a lot of different parts and with reliable experience, but maybe for some, how to say this, for some applications that are really critical, you will not want to rely on the process qualification. You want to qualify each part, maybe to be able to ensure a little bit more of the quality there. So regarding the process, typical defects, if you have not calibrated your process parameters the right way, you can have porosities and lack of fusion in there. So basically you're starting to induce some small cracks in your material that can lower the mechanical properties. If you're trying to improve the surface quality, you most likely will play on the contours on the parts, and you can have subsurface porosity, either created by keyhole effects or just because the offsets in your contours are not calibrated the right way. So those two things, I would say, are mainly dealt with the proper calibration of the process parameters. For most of the machine users, the process parameters are something that you buy on shelf. You buy a system on manufacturer and you say, I want to use this material, and you buy the parameters. So it's kind of a black box there. But if you're experienced enough, you will start playing with them in order to improve, either you want to improve the build rate or improve the surface quality. You need to always make sure that you're not introducing any new defect. Sometimes also you don't have the choice. You have to play with the parameters. So for us, when we introduce Camalloy on our system, so it's the material we're owning and we developed together with Airbus, there was no available parameters on any machine manufacturer. So we had to develop this ourselves, and we had then to prove it over time, over a lot of tensile testing, over a lot of parameter development, that we are now constantly reaching good quality. So this is about the process. And if we talk about a little bit about the part, what can happen in the part, there can be distortions, cracks, you can have also bad surface roughness there. So the main point there is that the part is also one variable in the process. Even if you qualify your process, each part is different. So each part will have a different, let's say, heat distribution. There will be a different heat transfer inside the part. This heat will lead to stress and deformation and can lead to cracks there. So this is why this shows a little bit the limitations of the process qualification. But you try to qualify a process that then will work for every part. It might not actually work for really specific parts. If you're talking about really small wall thickness or parts that are really challenging to print, your process qualification might not be enough. So this is why you still need to look out for distortions and cracks and other kind of defects. So therefore, you can use some methods like CT scanning or just even 3D scanning can be really helpful there and helps you to assess the quality there. Obviously, one of the biggest thing there is to print some tensile test probes or also microcut section test probes alongside the build job and to test those ones. But there's always the issue, as it is with the powder, of the representativity. Maybe you've printed something that didn't have the same cooling rate as your part because of a different lag time of your part, and then the microstructure, if you're in your tensile coupon, is maybe not the exact same one as in your part. So how can you make sure that the tensile test results are the same, what you're getting on your part are the same as in your samples? It's a little bit of an issue, and this is why I think what is mainly done in industry is to multiply the amount of those tensile test parts to make sure that, let's say, if on average everything is fine there, if none of them has a defect, then we are quite confident, and we're highly confident that all parts are in good quality. Otherwise, regarding the process, there's also quite a lot of tools that have been built inside the machine manufacturers, so we can have things like melt pool monitoring, also to have a look at each layer. Is it overheating or not? The systems are also providing job reports usually, where you can track all the parameters during your build, and you can evaluate all of this to see if your process has followed its right path, let's say. So this was it for the process. So we've now covered the whole triptych of how to, let's say, qualify the parts in AM, but then what does it look like on real life? So on real life, if we just take maybe one of our example there, so it's one of the few projects we are able to share. So we printed, it's an example of car exhaust that we printed in TI64. So I want to show you what concretely was done, let's say for this part as an example, was done to ensure the quality of this part. So we can directly see, I've made a little diagram of a timeline of what happened with this part. There's the first three boxes are with a different color because they are actually prerequisite. They are the three entities that we talked about. So the material, the first one is the material. We check the powder, we check the powder chemistry, we have powder certificates from manufacturer. Then we have the system, where we had maintenance that we perform every 6 months. We qualify each system on independent builds with a lot of tensile test specimens, so microcut section, density test all over the platform. So we have a qualified system, and then we have also qualified process parameters, which is linked to the other one. We have also a lot of data. So over the last few years, we have more than 400 or 500 test jobs that were printed. We have consistent data that really shows that our mechanical properties are consistently good. But this doesn't mean that everything we're going to print in there is going to be good. So this is why for each job, we have then the job report during the manufacturing. We also have pictures being taken there. We also have all the data that is generated in the machine that are going to help us to assess if everything happened well there. One thing that I didn't mention is that we can never really split the heat treatment and the AM process. For us, they're not the same process. They are two different processes, but we always assess the quality of a part that has been printed and heat treated. So for distortion reasons and also for mechanical properties reasons, you will want to heat treat all of your parts there. So during this process, we also have then certificates from the machine manufacturers. We also have like data that is generated. We can check that the heat up rate was good. If you have also reactive materials, you can check that the oxygen concentration was good, and then you're able to assess the quality there. Then you would have also other things that we should not underestimate is just the visual inspections. So we actually have multiple inspections also during the post-processing of the part, because it's something we're not gonna tackle here, but we need to constantly inspect the parts before and after the support removal. We do also some 3D scans that help us to check if anything was out of tolerances. And then we also perform those tensile testing where we get reports. Only after this, we are able to say that the parts that we are gonna deliver are, let's say, in quality. There's always one of the challenge there for the tensile testing that we sometimes need to make a compromise between the lead time and the proof of quality. So we have consistent data that shows that all parts are, let's say, always within our requirements. but sometimes we are not able to wait to get the final test results of this particular build before delivering to our customers. That's especially the case in motorsports there, but usually there's an agreement with the customer, we get the results right afterwards, and as soon as we get them, they are sent to our customers, and we are able to make sure to check that everything happened fine there. So that is it as a kind of example of what is currently happening. And the last point that I would like to openly discuss with you is what can we expect from the future there. So there's a lot of exciting things that are happening in there, and we're trying to stay up on track on everything that will show up in the future. Some of them are a little bit exotic, I would say. Some of them are really close to be released, but there's a lot of things that will help to assess the quality of AM components even better, even more efficiently in the near or long future. So one thing we are always talking about is about process simulation. Process simulation is really helpful for us, especially when we are tackling really tricky builds, tricky components that are prone to deformations, which is one of the defects in the parts. But we have heard and we are expecting to see maybe in the long-term future, to see a process simulation that will be able to predict the porosity in some areas. So by the process itself, you have some areas that are more prone to heat pile up, and this will lead up to possibly more porosity in those areas. So maybe in the future we'll be able to have this slightly improved. So there's also some kind of exotic things. People try to detect cracks in the build jobs thanks to vibroacoustical methods there. So basically you have a kind of microphone in your build chamber that is listening to the print job, and if you hear anything, then you're able to at least tell in your report, watch out, there was something happening at this layer. We don't know if it's good or bad. And then you can have a better look on your part, maybe with CT scan, or also looking at just the pictures of the print job, seeing if anything displays there. And it's just one more input there. Then also one of the things that we can never stress enough is about the understanding of the process parameters. A lot of people are working into this. A lot of R&D labs are working into understanding more about, let's say, things like the formation of keyholes, or how for defined materials, what are the thresholds for the energy input to not have any porosity, but we also do not want any overheating. So there's a lot to work in there. Then the next one is a little more controversial. It's about the process parameter live adaptation. So there is, some people would not want to have this at all. Some people would love to have this. You have maybe the possibility in the future to look at your process live and see if you have any overheating on some area. Maybe you can, on the next layer, go on this area with maybe slightly reduced laser power or slightly increased speed, in order to reduce the energy that you're putting in an area that has already overheated. Obviously, you need to do this within a certain parameter window that you have defined to make sure that what you're printing is still good quality. But this could help maybe to provide better output from the systems, but this would also then create more complex data to analyze after a build. Yeah. Last point also want to mention, and that will close out my my presentation, is about the powder bed inspection. It's something that I think a lot of people are not really aware about when we're talking about AM, is that a lot of things can happen inside your print job. Physically, the parts can actually move during the print. We are talking about really extreme cases there, but parts can slightly shift on one direction or another, and then this can create porosities, or sometimes you see it at the end of your build job, sometimes not. And we would hope also, and a lot of people are working on that, to be able to detect those shifts in the print job and be able to then have an accurate inspection on that if that ever happens. Obviously, the goal is to minimize those things and make sure that it doesn't happen, but sometimes it does happen. Then we need to be able to quantify how much did the part shift. If it shifted and shifted back, then you're able to you will be able to say to give it a go, no go, or maybe take a deeper look on that. So that was basically all, let's say, my expectations for the future of the quality in AM, and that actually then finishes what I wanted to give you the outlook of, and then I'm gonna start with taking your questions. So if you have any questions, don't hesitate to post them here, and I will answer them. So I already see quite a lot of questions. So the first one from anonymous attendee, which part of the quality triangle is, in your opinion, the most difficult to keep consistent? So I will say, I will start answering, to me, the easiest one is the material. I mean, I wouldn't say it's easy neither, but I would say it's the easiest one. But the trickiest one to me would be the process. The process is, there can be a lot of things happening. You never know if you have calibrated your process perfectly for a test part, but then when you just slightly change your part, what you have calibrated is maybe not the optimal there. Let's say, even with a calibrated process, even if the system is delivering exactly what it's supposed to be, your laser power is on point, your calibration is on point, the laser is going exactly where you want, the platform is dropping by exactly the layer thickness you want. If your process is not perfect, then you might not get the right quality. So next question, do you perform, from David Maas, do you perform or have you considered any in-process inspection other than male pool monitoring? We've looked into this, but so far, I don't think there is anything that could be better than male pool monitoring on the market. If there is some, feel free to come to us and tell us about it. But so far, from what we've looked into, the male pool monitoring is most likely the best thing to, it creates really complete output. After your print job, you can have even a thermal history of your print, which you can maybe in the future also couple with simulation there, because then you can actually simulate what you're actually not seeing. So the male pool monitoring, you're visualizing one layer, and you can actually look at both the temperature, and also you can look at a lot of things in there, and you could couple this with simulation and then look below there. So just to answer your question, no, we've not considered anything else from the inline inspection, so in-process inspection so far, because this is most likely the best thing there. Then next question from Wolfgang Käfer. Does your CT allow to look inside the parts, example to see cavities? Yes, of course. So the CT scanning that we are performing there usually has a voxel resolution of, I think, 66 micrometers. So basically we're able to detect every porosity that is bigger than 200 micrometers in diameter. So this is just, let's say, for the standard CT scan. If we are talking about more micro CT scan, we're able to focus the CT scan and get better resolution on some areas, but then we might not be able to scan the whole part there. And actually then we're able to spot all those porosity, and then we have go, no go criteria depending on the applications. There's always porosity in your material. The only question is how big do you allow them to be there. Next question, I take them as they come, from Pranav Patil. Do you use any simulation software for distortion compensation? And if yes, what are the results predicted by software and actual? So we have benchmarked all of this, especially, so we've used a lot of NetFab there, and we keep using it there. The process simulation is currently really good. We have one of the challenges there is that we're printing a lot of scamalloy, and there's no material card totally set with NetFab with scammers, so we have developed our own one, and we have results that are good. We are able to predict distortions on our parts. Let's say it's not quantitatively, it's not strong enough, but it really gives already a really good input for us to change the setup in our parts when we see that it's not optimal. And therefore, but the main, I think, challenge there is that process simulation still takes a little bit of time there, and if we have one print job with 30 different parts, we cannot afford to simulate everything, so we'll just pick the most complex ones, and for the rest, we'll have to rely on the experience there, and also all the inline quality inspections just to make sure we are delivering the best.
No, I'm playing the bad guy, so you'll get another 2 questions.
Okay. So I'll pick a long one then to make it last. From Stefano Scaramuzza. Sorry if I'm pronouncing not right. Do you think that vibroacoustical analysis of parts will really be feasible? I expect that this would be doable only for massive parts solidly connected to the build platform. You example parts, bracket, exhaust would be able to exploit these systems. So I've listed it as kind of an exotic way of performing QA. It's just, I think it's a good example of seeing how we could kind of think out of the box and perform and improve the current things. But regarding your question, I truly think this can help. We've seen a lot of parts which seemed to be simple and that didn't have any strong connection on the platform that can still slightly distort. And there's both sudden and slow distortions, and those sudden distortion can happen just when you have a tiny bit of support that breaks on a part that can be tiny. So even if the part is not massive, those things can happen, and those cracks, maybe we could then hear them and track them during the print job. So then a last question from Jürgen Silvanus. So is sourcing powder from different suppliers a quality risk? Yes, it actually is. So basically we need to try, we try to have the same norms every time when we are getting powder from a supplier, to have obviously the same requirements on them. And it's definitely feasible, because I think regarding the powder, this is where the standards are the most advanced there. A lot of people are currently, there is usually a consensus on what kind of powder chemistry you need, what kind of powder size distribution you need there. So it is a risk, because then you need to control multiple suppliers, but it's also something that is good, because then you have also a backup solution. If you have your main supplier is maybe unable to deliver and you need to print and you're lacking material, if you need to then requalify from scratch a new supplier, that is a challenge. Let's say you cannot just give requirements to a powder supplier and get it. You need to get first samples, analyze it, and get samples and do test builds with it. So we are really qualifying our supplier like this, and our optic is to have multiple powder suppliers every time, but there comes a little risk associated to this, as you've said it, because yeah, then you have more things to control there. So
thanks, Anu. I think I need to stop it here, but we will take the questions with us and answer them afterwards. So yeah, then it just stays with me to say thank you to everyone who attended, and a special thank you to Anu for this really good presentation and all the insights into quality in AM.
Thank you, Angela, for hosting me.
You're welcome. And for all of you, the next coffee break will be in 1 week, and we will highlight the topic of, let's say, differentiating between ALSI10 and Skalmeloy, and why I would say it's a false opinion to just say Skalmeloy is more expensive than ALSI10, because looking at certain applications and designing for Skalmeloy, you will hopefully see the complete opposite next week. So yeah, looking forward to seeing you next week, and have a good afternoon. And yeah, see you then next week.
Good afternoon, everybody. Bye.
See you, bye.